In this section, we're going to look at systems of linear inequalities, and to find the solution set for these, what we're going to do is graph each of the inequalities separately and then look at where their solution sets intersect. So let's look at our first example. We have two inequalities. The first one is x plus y is less than 5. The second one is 2x minus y is greater than 4. So we know that this is going to be a section of the coordinate plane. This is going to be a section of the coordinate plane. We'll graph each of them separately and then look at where their graphs intersect. So first of all, x plus y is less than 5. We know that the boundary line for this inequality is the line x plus y equal 5. And since my inequality is strictly less than, I'm going to graph the boundary with a broken line. So let's go up here to our little coordinate system, and I'll graph the boundary using a broken line. Now I see that the origin is away from the boundary, so I'll test the origin 0, 0 in my original equation. X equals 0, y equals 0, then 0 plus 0 is 0, which is less than 5. That's a true statement. So I know that my test point, the origin, lies on the solution set side of the boundary. So I know that that inequality is all the ordered pairs below the boundary line and looks like this. My next line is 2x minus y is greater than 4. I know the boundary for this inequality is going to be 2x minus y equal 4. It will have a y-intercept at negative 4, so 1, 2, 3, 4. That point will be on the boundary, and an x-intercept of 2. My inequality is strictly greater than, so I want to graph the boundary with a broken line, so I'll do that. Should look like this. And I hope that these colors will show up for you. Now, I'll test the origin 0, 0. In my inequality, 2 times 0 is 0, minus 0 is still 0. 0 greater than 4 is a false statement, so I know my test point, the origin, does not lie on the solution set side of the boundary. Therefore, the solution set for this inequality must be everything to the right of the boundary line. So that will look like this. Now, the solution set for this system of inequalities is going to be all the ordered pairs that lie in this solution set region and also in this solution set region. So that will be everything to the right of the blue dotted line that's also below the red dotted line. So that's going to be everything inside this region here, and that will be the solution set to that system of linear inequalities. So you can see what I've done here is I've graphed the solution set to the system of linear inequalities by graphing each of the inequalities separately and then looking at where their graphs intersect. So this region that you see right here, which is below the blue broken line and below the red broken line, that's the solution set to the system of linear inequalities in two variables. Let's take a look at another one of these problems. My first inequality is y is less than 1/3 x plus 2. Okay, let's graph the boundary line here. Y equals 1/3 x plus 2. It'll have a y-intercept of 2, so let's just write that down. Here's my y-intercept of 2, and it has a slope of 1/3. So if I go up 1 and over 3, I'll be back to another point on that curve, or that straight line. So let's see, my inequality symbol is strictly less than, so I know again I'm going to have a broken line. Let's see if we can just kind of sketch the graph of this right here. Here's a nice broken line. And let's see, the origin 0, 0 is off of this line. I can check the coordinates of the origin in this inequality. 0 less than 0 plus 2, that's 0 less than 2. So I know I get a true statement. The origin is on the solution set side of the boundary. So this time I'm just going to draw in some little arrows that show me which way this solution set goes. My next line is y is greater than or equal to 1/3 x minus 1. The boundary will be y equal 1/3 x minus 1, have a y-intercept of negative 1. Also a slope of 1/3, so if I go up 1 and over 3, I'll get to another point on the line. Actually, the same slope as my other line, so the lines just have to be parallel. Let's see if I can do that here semi-accurately. Won't be a great job, but you'll get the idea. Okay, again, the origin is not on the boundary line, so I can test its coordinates in my inequality. 0 greater than 0 minus 1. So is 0 greater than or equal to negative 1? The answer is yes. So I know the origin lies on the solution set side of this boundary. So the solution set is everything above the blue broken line. And since I'm trying to graph the solution set for this system of linear inequalities, I want all the ordered pairs that do this and also do this. So they have to be below the red line and also above the blue line. Well, that's going to be everything that's in between the two lines. Now let's see, I think I made one little mistake right here. As I'm doing this, I realize this inequality symbol is greater than or equal to, so no, I don't want a broken line down here. I want a nice solid line. So let me just draw that in. So everything in between the two lines, not including the red line, but including the blue line. So that will be my solution set for this system of inequalities. And you can see that I did the same thing as I did on my first problem. I graphed each inequality separately, and then I looked at where the two graphs intersected. I didn't want to make this quite as messy, so I just used little arrows showing the direction of the solution set for each inequality. Then I just reasoned that this part in here is going to be the part that they have in common. Made a little mistake right here when I drew the blue line as a broken line. Should have been a solid line. I corrected that in the end, so everything's okay. That's the solution set to this system of linear inequalities. Let's try another one of these problems. This one should be pretty easy. We have x is less than or equal to 4. Okay, I know the boundary for that is going to be the vertical line x equal 4. So I'll just go over here to 4, draw a vertical line with a solid line since it's less than or equal to. There's my boundary line. Okay, and I know I want all the ordered pairs x, y whose x coordinate is less than or equal to 4. That's going to be everything to the left of this boundary line. So I'll just draw in these little arrows to show that. My second inequality is y is greater than negative 2. So I'll just go down here to negative 2 on the y-axis. I'm going to draw in a horizontal line using a broken line because my inequality symbol is strictly greater than. So here's my nice broken line. And I want all the ordered pairs x, y where the y coordinate is greater than negative 2. That'll be everything up above this broken line. Okay, so I just ask myself now, where are all the ordered pairs x, y that are both less than or equal to 4, where x is less than or equal to 4, and at the same time y is greater than or equal to negative 2? Well, that'll be the intersection of the two regions I have here, everything that's to the left of the blue line and also above the red line. So that will be everything that's inside here. So this region that I have inside here, that's the solution set to this system. It includes the blue line. It does not include the red line, and it's everything in that little sort of square quadrant-like thing that we see. So it might have looked a little more difficult at first just because of the simplicity of these equations, but it's really not. We know that boundary line is going to be a vertical line. All x greater than or equal to 4 is going to be this way. And less than or equal to 4 is going to be this way. All y greater than negative 2 is going to be up here. That really looks like the region of the coordinate plane where we have all the ordered pairs x, y, where the x coordinate is less than or equal to 4 and the y coordinate is greater than negative 2. Let's try another one of these problems. This time my system consists of 3 linear inequalities in 2 variables. So I'll just go ahead and graph each one of them, and then I'll look for the intersection of the regions, the region that's the intersection of all 3 graphs. First of all, x plus y is less than or equal to 4. Boundary, x plus y equal 4. So I'll just go over here and call that 4. That 4. I'll draw a broken line. No, I'll draw a solid line between them because it's less than or equal to. The origin is not on the boundary. I'll test the coordinates of the origin in the equation, in the inequality. 0 plus 0 is 0, less than or equal to 4. That's a true statement. That means that the origin lies on the solution set side of the boundary. So I'll just draw arrows showing that it goes this way. Next, this inequality, x is greater than or equal to 0. Well, that's going to be all the x coordinates that are positive. Well, that will be everything from the y-axis on over. So the boundary will be the y-axis, and I'm looking at all the ordered pairs over here in quadrant 1 and quadrant 3, including the y-axis because this is greater than or equal to 0. Y greater than or equal to 0, well, that's everything with all the ordered pairs with positive y coordinates. That's going to be everything from the x-axis on up. So that's everything up in this direction. Now think for a minute, where are we going to find the intersection of those three regions? Everything above the x-axis, to the right of the y-axis, and below the line x plus y is equal to 4. Well, as you might expect, it's going to be everything that's inside this little triangle, because here are all the ordered pairs with a positive x coordinate, positive y coordinate, and x and y coordinates where x plus y is less than or equal to 4. It includes this part of the y-axis, this part of the x-axis, and this part of the line, x plus y is equal to 4. So you can see I graphed this system of linear inequalities in two variables the same way I graphed the other ones, even though I had three inequalities. I graphed this inequality, this inequality, this inequality, and then I look for the region that's the intersection of those three graphs. In this case, I used my little arrows just to show the direction that each of the separate graphs or solution set regions was, just to make it a little bit neater. But you can draw lines in different directions, whatever way you want, just so to be able to tell yourself where the intersection of those regions are. So that's a look at graphing systems of linear inequalities in two variables.